Good morning, dear colleagues. So today we will continue our seminars and we will solve some tasks. We will make some calculations. And today the main topic will be the attenuation of the fluxes of alpha, beta particles and gamma quanta. So we will see how to calculate how many particles will go through the material, through the shields. And for this, we have to remember two things. First, it is how the alpha particles are attenuated, beta particles, monoenergetic electrons, and gamma quanta. And to remind this, we'll start with a simple task. So we have parallel fluxes of particles of three kinds. Monoenergetic electrons, beta particles, and alpha particles. And they go through the aluminum shield or aluminum screen. And the thickness of this screen is 1/4 or 0.25 of the maximum range of beta minus particles. And the energy of electrons, alpha particles, and the maximum energy of the beta particles are equal to 0.7 mega electron volts. So the question is how many or what is the fraction of these particles that are retained by the shield. For this we have to calculate how many particles will go through the shield, and of course as far as it is information about the maximum range of the beta particles, we have to know this range. And for energy of 0.7 mega electron volt, the maximum range is given as 250 milligram per squared centimeter. It's quite a strange unit for the distance, yes, for the size. So these units are used because from this we can recalculate the linear size of the screen knowing the density of this material. So normally this linear size, let's call it L, will be this R max, for example, multiplied just by the, no, in this case it will be divided by the density of the material. So for example, if we have an aluminum screen, we can calculate this thickness for beta minus particle as 250 milligram per squared centimeter divided by the density of aluminum. The density of aluminum is 2.7 gram per cubic centimeter. And we see here is a milligram, so we have to convert either milligram to gram or gram to milligrams. So let's convert grams to milligrams. So it will be 2,700 milligram per cubic centimeter. So it will be so 250, yeah, 0.0926, let's say, centimeters. So it will be roughly 1 millimeter. Okay. Now we know the thickness of the material. We know the maximum range of the beta particles, and it is given for us that it is only 0.25 of this maximum distance. So let's call it L max also. So now we can calculate the thickness of the shield. It will be 0.25 multiplied by L max. And it will be 0.023, let's say, centimeter. Okay. So for monoenergetic electrons, the maximum range will be the same. Will be roughly 1 millimeter. For alpha particles, we should remember that the flux of alpha particle, so let's call it flux of alpha particle, and initially it is 1, and here's maximum range of alpha particles. The flux of alpha particle decrease as this, so all the alpha particles they retained by the screen, and all the particles, all the alpha particles are absorbed by the screen at the maximum range of the alpha particles. So if the thickness of the screen will be larger, like here, for example, is the screen, that means that the flux of alpha particles that go through the screen will be 0. So no alpha particles will go through the screen. If the screen has a thickness smaller than the maximum range of alpha particles, that means that all the alpha particles will go through the screen. That means that 100% of alpha particles will go through the screen. For monoenergetic electrons, it is just a linear dependence of the flux on the maximum range. So it is quite simple to calculate how many electrons will be stopped. So if the thickness of the screen is 0.25 of maximum range, that means that only 25% of the electron will retained, so will be absorbed by the screen, and 75% will go through the screen. For beta particles, it is a bit more complex dependence. So, max. In the initial range, before, if the thickness of the material is less than 0.3 of maximum range, we can simply calculate the attenuation coefficient as exponent in the degree of minus mass coefficient, mass attenuation coefficient multiplied by the thickness of the material. So we know that the thickness of the material is only 0.25 of the maximum range, so we can use this formula to calculate the attenuation of beta particles. So for this we have to know attenuation coefficient, and we can look it in the database. I will also send you these tables where you can see these maximum ranges for different particles. So for beta particles with the maximum range of 250 or with energy of 0.7 mega electron volts, the mass attenuation coefficient mu is equal to 23 squared centimeters per gram. So now we just put these numbers in the equation, so it will be exponent minus 23 centimeters squared per gram. For D, we should take the range that is expressed in units not in centimeters, but in gram per centimeter squared. So we know that it is only 0.25 of the maximum range, and the maximum range is also 0.25 gram per squared centimeter. So from this we can now calculate it easily. So it will be 0.24, let's say. So this value, as you can see, is different from the values obtained for monoenergetic electrons. In this case, for beta particles, only the fraction 24% of all the beta particles will go through the screen. So that means that 0.76 will be stopped by the screen. Okay. So, and what about the alpha particles? Will they go through the screen, or will they be stopped by the screen? In principle, the range, the maximum range of alpha particles is in the range of few, let's say, if we talk about the solid material, it is 10 to, I don't know, 100 micrometers. Usually even less, so it is around 40, 50 micrometers. But let's take 100 micrometers. So it is the maximum range of alpha particles. And we know that the thickness of our screen is 0.23 millimeters. That is equal to 230 micrometers. So thus we can see that the thickness of the screen is larger than the maximum range of the alpha particles, and thus 0% of alpha particles will go through the screen. That means that 100% of the alpha particles are stopped by this screen. So this is our first task, and we will go further. The next task. We have parallel fluxes again of monoenergetic electrons, alpha particles and beta particles that are going through screens, different screens in this case. And the thickness of these screens are equal to 0.6 of the maximum range of each type of the particles. And the question is what the fraction of electrons, alpha particles and beta particles will go through the screen and will be retained by the screen. So in this case, again, I will remind you again this dependence for alpha particles. So flux of alpha particles 1, and maximum range, we know from the task that the thickness of the screen is equal to 0.6 of maximum range of the alpha particles. So it's here. That means, again, that 100% of alpha particles will go through the screen. That means that 0% of alpha particles will be retained. So for alpha particles, it is always quite easy to calculate how many of them will go through the screen. Now for monoenergetic electrons. Again, it's quite simple. If we have a maximum range, we have linear relationship, and we know that it is 0.6. That means that only, so here it will be 0.4 of the let's call it 40% of monoenergetic electrons will go through the screen. That means that 60% will be retained. We can calculate this attenuation coefficient for electrons as 1 minus distance or thickness of the material divided by maximum range. So if it is 0.6, 1 minus 0.6 will be 0.4, and this coefficient, attenuation coefficient, tells us how many particles will go through the screen. So it is again quite simple. And for beta particles, I remind you that we can use this equation only if this distance is smaller than 0.3 of maximum range. And we know from the task that the thickness of the screen is 0.6. So we cannot use directly this equation. In this case, we have to use the experimentally determined dependence of the attenuation coefficient on the ratio of d to the maximum range of the beta particles. Again, we can look here. We can find that we know that this ratio by task is 0.6. So we should find this value on our horizontal x. So it is 0.6, then we will go up, and now we see that the attenuation coefficient in this case will be 0.02. Again, it is very different from the monoenergetic electrons. For the same screen, will stop 40% of monoenergetic electrons, and will stop 98% of the beta particles. So 2% will go through. It is so because we remember that the spectrum of beta particles is not a discrete, but it is continuous spectrum with maximum energy. It's for beta, number of beta particles. And we see that there is only a small fraction of beta particles with this maximum energy that will go to this maximum range of the beta particles. But a lot of beta particles have smaller energy. That means that they will be more efficiently retained by the screen with even smaller thickness, with smaller sizes. So it is the important difference between the monoenergetic electrons and beta particles. We cannot easily calculate the attenuation coefficient for beta particles. We either should use this graph, this experimentally determined dependence, or if the thickness of the screen or the thickness of the air or any other material will be smaller than 0.3 of maximum range, we can use this equation. So now the next task looks very simple. We have to determine the maximum range in centimeters for beta particles that are emitted by phosphorus 32 in air at normal conditions. So to solve this task, we should know the energy of the beta particles that are emitted by phosphorus. This maximum energy is given in databases, so we know this energy. And then, knowing this maximum energy of the beta particles, we should go to the databases and find the maximum range for beta particles with this energy. So I already did it. So I found this maximum range. And as far as we know, this maximum range in milligram per squared centimeter. So it is quite easy now. We can calculate this distance in centimeters by dividing the maximum range by the density of the material. And the density of air, we can calculate it because we know that it is normal conditions. We can easily calculate it by dividing the molar mass of air, the average molar mass of air, by the molar volume for, let's take for example, the ideal gas, 22 point. So for air, the average molar mass is 29 gram per mole, and the molar volume, it is 22.4 liters or cubic decimeters. It will give us 1.29 gram per cubic decimeter, or it will be the same as 1.29 milligram per cubic centimeter. We know all the required values now, and we can easily calculate this value. So it is 779 milligram per squared centimeter divided by 1.29 milligram per cubic centimeter. So it will give us approximately 604 centimeters. So you can see that for highly energetic beta particles, the maximum range in air can be very large. So it is 6 meters, the maximum range for beta particles. So if you have a source of the beta particle, source of the phosphorus 32 at your workplace, at your table, that means that the beta particles can reach you at the distance of 6 meters. That's why when we are working with the sources of the beta particles that emits highly energetic beta particles, we have to use special screens, special shields to stop them. Because even with your hands, you cannot, the thickness of the air will be not enough to stop all the beta particles. Okay, the next steps. Again, we have to calculate now the minimum thickness of a screen made of plexiglass or organic glass with known thickness, with known density, and we have to calculate this thickness to stop completely the beta particles emitted by strontium-89. Again, to solve this task, we should know the energy of the strontium-89 and the maximum range from databases for this given energy. Oops, sorry. Again, we know everything. We know maximum range of the beta particles, and now we have to calculate the thickness of this screen. How to do it? We have to take this maximum range and calculate this range in centimeters, simply by dividing maximum range by the density of the screen again. So it will be 666 milligram per square centimeter divided by, again, we should convert grams to milligrams, so don't forget to do this. So it will be 0.62 centimeters. Oops. That means that the thickness of 6.2 millimeters of the plexiglass will be enough to stop completely the beta particles emitted by strontium-99. So there is a dot. Yeah. If we compare it with air, for example, we will see that the maximum range of these particles in air will be 500 something 16 centimeters. So again, at a distance of 5 meters, the beta particles emitted by strontium-89 can reach the researcher, for example, or any other objects. And with use just of this thin, only 6 millimeters plexiglass screen, you can stop completely all these beta particles. So again, it is quite an illustrative example of why we should use special screens and how they are efficient to stop even such highly energetic beta particles. So the next task is we have to is dealing with the beta particles and gamma quanta. And now we have to calculate the attenuation for beta particles and gamma quanta emitted by potassium-40, so it is natural radionuclide. And these fluxes of these particles and quanta are stopped by aluminium plates with a thickness of 270 and 810 milligrams per square centimeter. Again, to solve this task, we have to know the energy of emitted beta particles and the energy of emitted gamma quanta. And from the databases, from the special tables, we can calculate the maximum range of these particles, the mass attenuation coefficient for beta particles, and the linear attenuation coefficient for gamma quanta. So, to solve this task, I would start with the gamma quanta, because it will be much more easy task. First of all, for gamma quanta, we should convert this thickness from units of milligrams per squared centimeters to linear sizes. So L1 will be 270 milligram per squared centimeter divided by the density of aluminium, and again we have to express it in milligrams per cubic centimeter. Thus, it's quite easy, it will be 0.1 centimeter. And L2 will be 810 divided by this, so it will be 0.3 centimeter. Okay, and now attenuation for gamma quanta in first case will be exponent. Yes, for gamma quanta we always use this equation. There is no limitations, thus it's quite easy. So we will take this 0.13 multiplied by 0.1. .987. That means that almost all the gamma quanta will go through this screen, and only 1.3% will be retained by this screen. In the second case, when we increase the thickness of the material 3 times, the attenuation will be not much higher. It will be 0.96. That means that only 3.8% will be retained. It is for gamma quanta, and we can see that these aluminium screens are not really useful to stop the gamma quanta, even with the thickness of 3 millimeter. And now let's calculate these attenuation coefficients for beta particles. And we know the maximum range, and we can see that even in the case in the first case of 270 milligrams per squared centimeters, this relationship 0.3 maximum range is not correct, because we can divide this 270 by simply 572, and this value will be larger than 0.3. Okay, so how to solve this task then? We have to take into account this graph. So we should calculate this ratio more precisely. It will give us 0.72. So we can take simply 0.5. And it will be here, or very close to this value, and so it will be something like 0.05, approximately 0.05. That means that 95% of all the beta particles will be stopped even with this first screen with the thickness of 1 millimeter. And what about the second screen with the thickness of 3 millimeter? We can see again that the maximum range of these beta particles is only 572 milligrams per square centimeters, and this second screen has a thickness larger than this maximum range. That means that in this second case, the K value will be equal to 0. That means that no beta particles can go through this screen. So 100% of beta particles will be stopped. Again, it is quite illustrative example of how different particles, beta particles and gamma quanta, are stopped by the same material with the same thickness. And now we will go further. The next task, we have to calculate for the strontium sample the attenuation coefficients for beta particles that are emitted both by strontium and yttrium-90. In this case, strontium-90 and yttrium-90 are in a secular equilibrium, and it is very important to know the whole chain of the decay. And in this example, we will see that if you, for example, you know that there is strontium-90 in your sample, and you calculate the thickness of the screen that is sufficient to stop all the beta particles emitted by strontium-90. But if you forget that there is also an yttrium-90 with the beta particles, the maximum, sorry, it's not the energy of gamma, it should be energy of beta particles emitted by yttrium-90. And you see that this energy is much higher, much larger than the energy of beta particles emitted by strontium-90. That means that the maximum range of these particles is much larger than the maximum range of beta particles emitted by strontium-90. And if you will take into account only particles emitted by strontium, you will get the thickness of the screen that is insufficient to stop all the beta particles emitted by your sample, because from strontium-90 there will be accumulation or formation, generation of yttrium-90, and these beta particles emitted by yttrium-90 will easily penetrate through your shield and will give the larger dose rate, for example, on human body. So let's solve this task and calculate the thickness or the fraction of beta particles beta particles emitted by yttrium-90 through that will go through the screen that is enough or sufficient to stop all the beta particles emitted by strontium-90. For this, to solve this task, we know all the information. Again, we know the maximum energy of the beta particles. Information is specific for a certain radionuclide. And the maximum ranges and the mass attenuation coefficient, they are specific for a certain energy. So you can calculate this value from the tables easily. So let's calculate first, or we don't need to calculate the linear thickness, linear size in centimeters of this screen, because to solve this task we just need to know the maximum range, and it will be the thickness of the screen. And we see that in this case this ratio 9 divided by 1 will be less than 0.3 of maximum range for beta particles. And thus we can use this formula, and we can calculate now this value for yttrium attenuation coefficient. We'll take mass attenuation coefficient 4.45 centimeters squared per gram, and we will take the thickness that is equal to maximum range for beta particles emitted by strontium, milligram. And again, we have to remember to convert milligrams to grams. Thus, we have to multiply it by this coefficient. And the attenuation coefficient will be 0.18. That means that 42% of the beta particles emitted by yttrium-90 will go through this screen and can irradiate everything that is located from the other side of the screen. Just for information, let's calculate the density or the linear size of this material of this screen. It will be this value in centimeters. So it is 0.0726 centimeters. So it is not very thick screen, honestly. It is only 0.7 millimeters. But still, you can use this thickness as a walls of the container, for example, and again it will be not enough. It is good example of the first specular equilibrium, and the second again that you should take into account the whole radioactive chain, because you can miscalculate it, the thickness of the shield of the screen for safe operation with the specific source of ionizing radiation. So that is all for today. Thank you for your attention, and see you next time.